Thank you very much. Thanks. A pair of turtles mounted on a boat which is symmetric, Z2 cross Z2 symmetry, and I can position the turtles in any way you like. So they're facing each other, for example, and I can spin them clockwise or counterclockwise. Or maybe they have been having a fight, a tiff, so they don't want to talk with each other. That's quite sad. You can still spin them positively and negatively. Or maybe one of the turtles is in love with the other, but alas, affection is not reciprocated. You can still spin them one way or the other, no problem, and no surprise. But now, if you position the turtles like so, in an S shape, thereby changing the symmetry pattern, but please note that the center of gravity is still smack in the middle. That hasn't moved. Well, you know that turtles like to walk forward. I dare say you have never seen a turtle go backwards. So if you ask them politely and gently, because these are sensitive animals, to please go forward, they are willing to oblige smoothly as before. But if you try to force them to go backwards, they say, no, 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 we don't want to go backwards, and they spontaneously reverse the spin. No, 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 we really don't want to go backwards, and they reverse the spin. And it is not a question of left or right, because if I position them in the Z shape, what used to be the reductant direction is now smooth because they're going forward, and what used to be the favored direction, really, they don't want to go back. That is strange. I mean, whatever happens to the conservation of angular momentum and all that. Now, you're all wondering what happens if I position the turtles like this. Well, let's spin them, as seen from above, clockwise, like that. And, well, then this turtle would go forward and this turtle would go backward. So happy and unhappy, they have a vote each. Democratic turtles, they cancel each other. And then the other way, happiness and unhappiness reverse, and their rotation can also reverse. It is very great stuff. Now, this phenomenon was observed about 100 years ago, a little more than 100 years ago. Since then, lots of papers have been written about this. And most of these papers seem to be wrong. And the reason is they study always this kind of thing. This is a popular model that you can get from museums of science. And this does have a rotational preference. We call them chiral preference, chirality. It wants to spin this way, but the other way, it rattles and stops and goes back. No, it really doesn't want to go back. But you see, if you look at the surface, it is quite difficult to see on the camera, but there's a sort of mountain ridge-like asymmetry that is running over the surface, so that the surface is not symmetric anymore. So many people started from the assumption when modeling this system that the surface asymmetry was of the essence, but in fact, it has nothing to do with this behavior. You can have a completely symmetric surface. The only thing that matters is that the mass distribution be skewed, or to be a little technical, the ellipsoid of inertia should be misaligned with respect to the geometrical axis. In order to drive home that point, I had this made in Paris. This is a completely symmetric body. In fact, it has front and back symmetry as well. Nonetheless, it does have a preferred direction. You see, clockwise, it really doesn't want to spin, but counterclockwise, that's no problem. You see, clockwise, it does not want to spin, but it wants to spin counterclockwise. Now, if I rub it against my shirt, rub it very carefully, it spins clockwise, not counterclockwise. Counterclockwise, which it used to like, it doesn't like anymore. It's now spinning clockwise, and counterclockwise, which you used to like, it doesn't like anymore. That's very strange, just rubbing against my shirt. If I rub it against my hair, it spins now counterclockwise, and clockwise, it refuses to spin. It's just like before. That's very strange. But if I rub it against my jeans, nothing changes. It is still counterclockwise, and clockwise, it really doesn't want to spin, so it stops and reverses. With some audience, I could keep going for 30 minutes, but because you're friends of mine, I shall reveal what's happening is that inside I hid a lead bar, which is skewed a little like this. So each time I carefully rub it against my shirt, I put it down like this, flip it over, and that changes the chirality. But you see, this shows that really the shape has nothing to do with it. It is this distribution of mass that matters. So you can make something like this at home or find it in nature. If you go hiking along rivers and beaches and so on, you might sometimes find longish pebbles. And in my experience, about 1 in 10 exhibit this kind of behavior, which is called chiral behavior, chair, that's Greek for hand, handedness. Right spin, left spin, different. And you see, in science, especially in the biochemical context, chiral structures have been extensively studied. Molecules that are mirror images of each other, so they differ only in being mirror image, so chirality, but one of them is harmless, but the other one is totally toxic and so forth. But these are structured, static things. Chiral dynamics, things that evolve in time, have not been studied so extensively, and this is, in fact, practically the only example. So it's a stone that I have brought, and the tendency of chirality is so strong that you don't even have to begin by spinning them. If from rest I tap a little bit, it spontaneously spins one way rather than the other way. Another way to make such a thing at home is if you are you old enough to remember those telephones that used to be connected to the cord and so on? Well, if you have one of those still, you disconnect it from the cord and attach heavy masses, a bit like those heads of the turtle sticking out with, say, batteries with Scotch tape or something like that. And if you put it on a smooth surface and tap a little bit, it will spontaneously spin one way rather than the other way. And if I position the turtles like this, naturally you imagine that they spin this way. Now, I'd like to share with you one key observation which cracks the back of this problem, which has been missed for many, many, many decades. And that's what I'm about to show. You see, if you think of this as some kind of boat, a boat can rock in different directions. It can rock back and forth. That's called pitching in nautical terminology. Or sideways. That's called rolling. That's the one that makes most people seasick. And finally, it can spin around the vertical axis. And we have now observed that pitching makes them go forward. Pitching feeds the energy into the forward spin. Indeed, if you try to force them to go backwards, you see that the pitching gets excited, followed by the reversal of the angular momentum of the spin. It's remarkable that people have been saying, so pitching is unstable. Very few people have asked themselves, what about rolling? Let's try rolling by tapping here rather than here. You see, if I tap here, they go forward, and that's pitching. What about rolling? You're about to see something that people haven't tried for 100 years. They go backward. It's behaving like reverse turtles. Yeah, they start going backwards. So I was cheating all of you a moment ago. I said that if you spin them forward, they spin smoothly, but that's not true. You see the turtles start rocking their heads, and that's rolling. As a result, they can reverse even from the forward direction. Did you see that? The reversal is quite weak because the friction is killing the motion before long, but they can reverse slightly but noticeably even from the forward motion. There is a lot of places in the literature that say forward motion is stable, backward motion is unstable, but that's not true. Both directions are unstable. As a result, this object can reverse multiply, forward, backward, if the surface condition is correct. One of the world records for the multiple reversals was held by those turtles, and it was achieved on the marble top table in a cafe next to the British Museum in London. And they reversed 5 times, back and forth, and I wanted to buy that marble top table with a research grant, but somehow the council said no. So this kind of thing is around us, and it's quite exciting to watch. Now, those are the turtles. Now, I'd like to share with you something about the names of those toys. You see, the popular name is Rattleback. Probably that's the one, if you have seen this toy before, that you have seen before. Also Wobble Stone or Celt, C-E-L-T, not Celt, but Celt. The story often told is that Celtic villages of 2,000 years ago were excavated by archaeologists who found such stones that have a preference, chiral preference to spin one way, but not the other way. Actually, so the instability in the spin. Perhaps they were talismans, perhaps magical objects, and so on. That story turns out to be completely false. The real story is much more remarkable. St. Jerome, the person who's sitting next to the lion, translated the entire Bible into Latin. As you know, that's the first canonical Latin translation of the Bible. And the book of Job, the chapter 19 and verse 24, Job says, Job is, as usual, complaining about various things. And he's saying that, well, I do all this, but I'll be forgotten soon, and I wish that my contributions are more permanently remembered. Well, it sounds like somebody else that I know. And he says in that passage, Stilo ferreo et plumbi lamina, well, Celte, this is the keyword that I italicized and bold-faced, sculpantur in silice. In literal translation, that my words were by an iron pen and lead or by something called celt graven in stone. Now, celte looks like the ablative of the Latin word celtus. In other words, by means of, by the instrument of something called celt. However, there is no such word as celt or celtus in Latin. So people thought on the authority of the Bible, of the Vulgata translation, that well, it must mean some sort of implement, like a chisel, with which you can engrave and so on. And so this word celt came into existence into the English language. But if you look at the same passage in Hebrew original, it says, Bet barzel ve'ofaret la'ad, that's the key word, batsuri hatzvun. And la'ad in Hebrew, as many of you know, means for certain, forever, or in Latin it would be certe, R rather than L. You know that the Japanese are incapable, notoriously, of distinguishing between L and L. So it turns out that this word celt came into existence because of a misspelling in the Vulgata Bible, and the Celtic connection have been made up with by antiquarians in the 18th century. How beautiful is that? Okay. We shall now, having violated the conservation of angular momentum, we shall now go on to violate other great principles of physics. Here's an egg. In fact, it's an artificial egg, but in case you have any doubt, it even says EG on the surface. The demonstration that I'm about to share with you works perfectly well with boiled eggs at home, on a wooden table, for example. Well, you know how to distinguish a boiled egg from a raw egg? You can spin it. A boiled egg, because it's a solid body, spins smoothly, but the raw egg doesn't want to spin because there's some sort of liquid stuff sloshing about inside which resists the rolling. However, if you keep coaxing the raw egg, it will eventually agree to start spinning. And once it starts spinning, because this angular momentum, tendency to keep rolling, is carried by the liquid stuff, it has the following curious property. You make it, somehow convince it to spin, and then you catch it, and half an instant later, you release the thing, and as you can see, a solid body stops and stays, put forever. But the liquid or the raw egg starts spinning again, which is an interesting experiment. So I encourage you to try this, but that's not what I wanted to show. What I wanted to show is how do you make an egg stand up? Well, have you spun an egg? What happens is, excuse me, it pops up like this. I'll do that again. It pops up. This is quite surprising. Why do we find it surprising? Because we learn at university in Cambridge and at primary school in Princeton that nature wants to lower her center of gravity as much as possible. You see, if you leave it like that, the egg lies flat there and in stable, static equilibrium with low center of gravity. This is unstable, that's stable. But it is a fact of nature, little noticed, and even less used, that a spinning object in frictional contact with a support has a tendency to raise its center of gravity. Another thing that I would like to point out is, you see, an egg has a bluff end and a sharp end, rounded end and a pointy end. You might have noticed that every time we spun, this egg stands up with the sharp end pointing up. It might be not so easy to see, but the sharp end is up and the bluff end is down. You might ask, well, if the egg wants to raise its center of gravity so high, why doesn't it stand upside down? Because that would be even higher center of gravity. There have been several papers about this, believe it or not, and which try to explain, other things being equal, why this happens. Very complicated and sophisticated perturbative analysis. But several years ago, I came in and finally resolved the issue and proved why it has been mathematically impossible to prove, and explained why it has been mathematically impossible to prove that the egg stands up always on the bluff end rather than upside down. And the reason is really profound, because it's not true. It's standing upside down perfectly well, like this. Okay, a toy that takes advantage of this property is this. You might have seen this. It looks like an apple. It's carved a little bit inside, and it doesn't want to look like a mushroom because it is heavy at the bottom, and that's the stable configuration. Now, can you make it stand upside down? Well, it's very difficult. But you remember, an object spinning in frictional contact has a tendency to raise its center of gravity. So let's spin this. And it pops upside down very beautifully. I can do the same thing with my left hand, pops upside down. For that matter, if you play golf, well, I have never played golf in my life, but I have published a paper on golf. So you see, I'm a theoretical golfer. And if you go, doing a round with a friend of yours, and you're about to putt your balls into the hole, and if you want to win, and if you don't mind losing your friend, then I suggest that you replace the friend's ball by this one, because when the friend tries to putt it, it goes all over the place, and then it doesn't really. It is a weighted ball, upside down, it doesn't really like. But let's spin this object. When I spin it, you see it's stable like this, upside down, it's unstable. But when I spin this, centrifugal force and all that makes it go wild, but suddenly it quietens down in stable spin. In that state, when I catch it, where is the center of gravity? It's at the top, not at the bottom. Indeed, when I release it, you see it flips over. So really, nature wants to raise its center of gravity when it's spinning. I'd like to then show you a rough explanation for those people who are mathematically inclined of what is happening. Here is the diagram of the angular momentum, and we shall introduce two approximations. First, we'll assume that the angular momentum tendency to spin is more or less constant. Indeed, in the beginning, it's spinning vigorously, and at the end, it's still spinning vigorously. So that blue arrow is constant, and theta measures the angle of inclination of the axle with respect to the vertical. And r is the radius of this shape, and we introduced another approximation, which is that this gap between the center of gravity, marked by the black dot, and center of curvature, which is the geometric center of this thing, white dot, there is a gap between. This is very important, this gap. That is, the object is weighted and shifted on one side. But that gap, we shall assume, is small compared with the radius r. Now, with that assumption, you see the following kind of thing. You see, because the object is spinning around like this, the left half of the page, this half, is coming out at us. And the right half of the page, that side, is going into the page of the picture. Okay. But you see that the point of contact with the floor is directly underneath the point of the geometric center of curvature. So that's in the right half of the picture, meaning that that point is sliding into the screen. The friction, which opposes the sliding, is coming out at us. Did everyone follow? So that point is coming out the friction is coming out at us. That's the conclusion that we have. So we have that kind of friction. But you see, if you have a body and you kick the bottom with friction or some other force, what does the body do? Or you have a tendency to get the body to spin in this direction, right? That means, mathematically speaking, that there's a torque which is pointing sideways towards the left, and it's approximately horizontal thanks to the approximation that this gap is small compared with r. Okay, so that's the torque. Now, we shall see how the component of the angular momentum changes along the axle. That's easy. That's L times cosine theta, and the time change in ddt. And it's due to the torque, the effect of the torque. And the projection of the torque along this axle is tau times minus sine theta. There's a minus sign because this direction and this direction are opposite. Well, we said that L is approximately constant. That's good news because we can take L out of the differentiation, and you get immediately that theta dot is, that's time change in theta, is tau over L. What is tau? Well, that's the torque. That's the radius times the force, constant of coefficient of friction times the weight, mg. And what is L? That's the angular momentum. That's equal to the moment of inertia times the angular velocity. Angular velocity we shall take, that's another approximation, as the initial angular velocity. It's the approximation that ultimately comes from the approximation that angular momentum is supposed to be constant. And this moment of inertia is written in a funny way. It has the moment of inertia has the physical dimension of mass times the radius squared. So I'm going to write it like this. I hat then is dimensionless. That number, you can look it up in textbooks, so you can calculate, turns out to be 2/3 for a spherical shell and 2/5 for solid ball. So let's estimate the tip over time then in this model. Well, what does it mean for this thing to tip over? Well, theta must change by pi. And theta is going to change because you see that theta dot is positive. That means because this vertical direction is constant, the only thing that can happen that makes theta increase is the axle to start tilting, and that's the tip-over mechanism. Okay. Tipping over then is pi, and you divide by theta dot. That's going to give us a tip over time. But wait a second, there's something wrong in here. When I made this deduction, I divided surreptitiously by sine theta. What if sine theta is 0? That's when theta is 0 pi. That is, in the beginning of this mechanism, and at the end, something goes wrong. So this approximation is what people in applied mathematics, and in particular Barenblatt and others, call the intermediate asymptotics. We hope that this kind of regime dominates and gives us the essential physics, but in the beginning, at the end, something ugly happens. But let's throw them out of the window and see what happens. So tip over time is pi over theta dot. Okay, so theta dot, there is some simplification. 1 pi over r cancels and m's cancel, and then you get this expression. Let's plug in some numbers. Pi is pi. What is I? Well, I said it's 2/5 or 2,000 something. It's approximately half. R, well, what is R for this kind of object? Well, it was quite small. I would guess 1 or 2 centimeters, so I put in 2 centimeters. Omega is difficult, so we shall come back to that. Let's figure out mu. Mu is the coefficient of friction, and there's a good way to measure what this is. You see, you put this object on the support surface and start tilting it until it starts sliding. The tangent or the slope of that critical angle at which it starts sliding turns out to be mu, the friction. It's actually static friction, not dynamic friction, but the difference between them is not that great, so we shall take that, and that's 1/3. And also, the gravitational acceleration g, you might have remembered 9.8, but that's because you're thinking in meters per second. If you're thinking in centimeters, as we did when I said 2 centimeters, it's about 1,000. Now, let's come back to omega. What is the spin rate or the initial angular momentum? You see, this is a little tricky, but because it's angular velocity, it's 2 pi times the number of spins per second, number of turns per second. Now, how many turns per second am I doing? Can you help me to estimate this? That's pretty fast, huh? And 1 second is a long time. 1 second, 1 second, 1 second, 1 second, 1 second, that kind of thing. Huh? When I spin it, how many spins per second? 1 second. Well, I think that it's spinning more than 10 times per second. But it's spinning less than 100 times per second. So let's take the average between those two limits. And what's the average between 10 and 100? We're tempted to say it's 110 divided by 2, but that's not the right average. That's the arithmetic average. Because we are multiplying numbers, we should take what is called a geometric average. We should multiply and take the square root, and that's about 30. So we shall take 2 pi times 30. And when you do the arithmetic, well, pi times pi is about 10, and so on, 1 0 drops. And the prediction of this theory, very, very crude theory, is that it's about 2 seconds. Okay, let's see 1 second, 1, 1, 1, 1, 1, 1. Hey, did you see that? 1, 1, 1, 1, 2. Pretty good, huh? Okay, well, that's very easy. Okay. I'd like to share with you then a final piece which grew out of this. Here is an object which was created by somebody called David Atchison accidentally in Oxford as a special object for that special somebody on that special occasion, but it turned out to be so special that I kept it for myself. It is a tippy top, and when I spin it, excuse me, it pops upside down. Oops, sorry, I'm going to spin it properly again. Okay, it pops upside down. So it is a fairly good tippy top, as tippy tops go. A moment ago, I said I can spin with my left hand. You thought I was showing off. I was, but there was a scientific point to this. I'm going to now spin it with my left hand. That is, give the initial spin exactly the same spin, but of the opposite sign. I'm going to spin it like this, not like this. And then what happens is that you see this thing keeps spinning. The axle has tilted immediately, and it keeps trying. You can wait. You can wait. You can wait. I've tried this with lots and lots of initial conditions with many, many different people and on all sorts of surfaces, you have in front of you what was for the longest time the first and only chiral tippy top. Namely, a top which spun one way tips upside down, but the other way it does not tip over at all. Now, as you saw, I was very glib about this model, and in fact, I can do much better than this in theory. And there are lots of papers out there, lots of models, and of course, my model is the best. I can calculate lots of things that other people cannot calculate, but none of the models out there, including mine, allow, never mind, and explain the existence of such an object. So there's a big gap in our understanding of tippy top. We don't know how chirality arises. Well, by this time, I think I can produce this empirically by taking wads of clay and hemispherical shell and so on, but there's no model at all at the moment. So this is probably the open problem, or certainly the most exciting open problem in classical mechanics. It's amazing that classical mechanics still has open problems. And by the way, if you talk to physicists and applied mathematicians around the world, most of them will deny the existence of this object because it's really perpendicular to the way we understand traditionally tippy tops. So that's what it is for you. Okay, let's move on to the next demonstration. So far, we have been producing all sorts of strange behaviors, but with a single object. Now, I'd like to start doing things where lots of different objects start interacting among themselves, multi-body problems. And in order to do so, I have brought here soup bowl that I borrowed from cafeteria in Cambridge University, and another box. It's a bit Chai Gruzinski extra, it says on the cover, extra Georgian tea. And when you open the lid, it says Kaiser Varivach Chai, how to brew a good quality of tea, very scientific instructions, but that has nothing to do with my experiment. I'm carrying around cedar balls inside. Now, if I put just a few cedar balls, 3, for example, and swirl the soup bowl, you can see that cedar balls circulate in the direction that I'm swirling. Please note that when I say swirl, I'm not doing this. I'm not rotating. I'm just translating in a circular fashion. But anyway, they swirl in the normal direction, the direction I'm making them circulate, and they circulate exactly in the direction that I'm swirling. Good. But now, let's increase the number of cedar balls. When I swirl this time, they start going in the opposite direction. Do you see that? I'm swirling this way, but the cedar balls are going this way. So there was a transition. With 1 ball, 2, 3, we have seen, 4 and so on, they circulate in the direction that I'm swirling, but 5 and 6, there's a lot of hesitation, and 7, there's definitely a tendency to start going in the wrong direction, and 8 and so on. This is what I would like to suggest as a toy model of something called phase transition. You know, when gas condenses to, vapor condenses to water, water freezes to ice, or vice versa, and so on. These are called phase transitions. But when we talk about phase transitions, we always think about an enormous number of degrees of freedom. This, on the other hand, has very few degrees of freedom, and we understand everything. And it is a bit like a phase transition in the sense that you see what's happening is that when you have few balls, those balls are effectively independent particles. They don't talk to one another. And what is driving their motion is linear momentum. That is, the wall is hitting them every once in a while, and they are sent in that direction. They are hit. That's all there is. However, when the order parameter, that is the crowdedness, increases, the neighbors start touching one another. And what happens is that, well, whatever momentum comes in gets scattered among the neighbors, so that's wasted. But what is not wasted is the rubbing. When the wall rubs, the ball rotates and transmits that rotation to the neighbor and so on. So neighbor-neighbor interactions, this now becomes an angular momentum-dominated regime. So there's a transition from linear momentum to angular momentum domination. And it's a bit like gas to liquid, because in liquid, molecules are in contact and can slide past each other, but they're quite bound among themselves. And to show you that it is really like phase transition, it's of course a toy model. If I keep increasing the density, then they freeze solid. You see, it's a bit like this. This phenomenon was discovered by Rayberg. Well, we shall do something even more difficult and really annoying, for mathematicians and physicists alike, which is in the form of those two. Can you see? No, we cannot see. So I think what I have to do, I have to solve the geometry problem, which I used to do this kind of thing. Here it is. OK, so now it's upside up. Sorry, otherwise you have to turn around. Those are two heptagonal-looking wheels. And I can guarantee that they're made of the same material. They have the same surface coating. They also have the same mass. And let me add a technical condition that the density function within each is constant. What do I mean? I mean that the distribution of mass within each is homogeneous. There's nothing hidden in there. I'm saying that it's not the case that there's more mass hidden in the spokes and there's a hollow hidden inside. Whatever you see distributed in volume is exactly where the mass is. Is that OK? So that's what they are. However, there's a big difference between them. When I try to roll one of them, it rolls very well, with alacrity, one can say, but the other one refuses to roll. One of them rolls very well. The other one really does not want to roll. And in case you're wondering, I can go the other way around. So this rolls very nicely, but this one really does not want to roll. This rolls. And yet, when you put them together and look through them, you can barely see, you cannot see the difference at all. So what is different? Huh? Sorry, is there a guess? What's different between them? And also, if you find a tiny difference, you should then convince yourself that that tiny, tiny difference can cause this qualitative difference in the behavior. Is that really likely? So what is going on? It's the same material, same surface coating, same mass, and the mass distribution within each is constant. There's, of course, something that I'm not saying the same. What's happening is that the one that rolls is a heptagon, 7-gon, but whose edges have been slightly bulged out to make them a little round. And the one that refuses roll is a straight heptagon. Let's see what the difference is going to be. This is the picture of a slightly bulged heptagon. And let's say the bulging is tiny, tiny, and mathematicians like to call it epsilon. In this case, epsilon is less than 0.1 millimeter. If you saw, by the way, do you all talk metric or 0.1 millimeter, whatever that is in feet and yards and so on. If the diameter is about 10 centimeters, it is less than 1 in 1,000. So that's small. But however small, you see, if you have a little bit of bulge, as the thing tries to roll, it wants to go from one vertex corner to the next corner. And as it rolls, you see, the point of contact can smoothly, continuously transit to the next corner because it's bulging, and it can smoothly go to the next corner. So that's good. In contrast, when epsilon, this bulge, is strictly 0, when you have a straight edge everywhere, then that's a disaster, because as the heptagon wants to roll, it effectively has to pivot around one corner while trying to go to the next corner. But while it's trying to go to the next corner, there's no contact. The entire edge is in levitation, and it's sort of leaning, and then until the next corner goes bang against the floor and dissipates and kills the motion, because there's no more energy left at that. So you have a discontinuous passage. This discontinuity happens, however small epsilon is, you can go continuously, but as soon as epsilon becomes 0, there's a catastrophe. This kind of thing is called singular perturbation. This is really one of the most challenging themes in mathematics, application of mathematics. You have a family of models that depends on the parameter, let's say epsilon. And when epsilon is not 0, when it's 0.1, you get some prediction. 0.01, you get the same prediction. 0.01, same prediction. 0.00001, same prediction. 0.0000001, same prediction. And so you think, OK, when epsilon is 0, it's the same prediction, but surprise, you get something completely different. The most famous example, as you probably know, is the Navier-Stokes equation. When the viscosity drops and becomes 0, the prediction that you get as the viscosity becomes 0, close and close to 0, but not 0, is a huge turbulence, a very, very messy pattern. But when the viscosity is 0, you get what is called an implicit scenario, and you can get a beautiful laminar pattern of potential flow. So the limit of the prediction is not what is predicted by exactly at the singular point. So this kind of thing is great, but you see Navier-Stokes is infinite dimensional, and this, again, probably has the world record for the smallest number of degrees of freedom of a real physical system that gives you a singular limit. Okay, now let's then, so far we have been producing singularity, but as a limit of models. Now I'd like to produce a singularity within the same model, and that is called a finite time singularity. When you drop a coin, you hear, Peter, do you have a coin? Does somebody have a coin? That sounds like a coin. Yes, I should pass around a hat. Thank you very much, Anna Rosa.
It'll get there, but not soon.
Maybe you all use, thank you very much. So, thank you very much, Joe. When you drop a coin, you hear this very characteristic shuddering noise. It's so characteristic that when you hear this noise in a restaurant, in a cafe, you know that somebody dropped a coin. Okay, thank you very much. And this is a very heavy coin. It's an exaggerated heavy coin, and it's huge. And so in order to show that I'm not lying, I'm going to go to Joe. And can you tell people that it is very heavy?
Very heavy.
Thank you very much. And so you get, I pay you a quarter for this. So because it's heavy, when I launch this coin, the motion lasts a long time. And because that lasts a long time, you can observe various features that escape our attention. It's going purely by its own inertia. I didn't do anything. I mean, I just launched it and stood back and watched. There's no magnet, there's no motor. It's going and going and going. And you can, interesting, there's a reflection light there. But anyway, it's going and going on its own. And you feel that something is accelerating. But you can note, if you're close by, that actually it's not rotating any faster. The rotation rate, spin rate is quite steady, but something nonetheless is getting accelerated. What is that? It turns out to be the flapping motion. It's going on its own. It's going. It's going much longer than I thought. But eventually it will come to a stop. And when it does, I'd like to invite you to not only watch, but to listen to the pitch that rises, the sound that comes out of this curious coin. Now, that's pretty. So whatever happened, something diverged, something went to a singularity in finite time. We'd like to understand what it is. Now, this object became a subject of, this subject became the object of, anyway, intensive study about 12 years ago, and lots of people wrote research papers, and one of them appeared in Nature, no less. And this paper said that this effect has to do with the friction of the air trapped underneath the disk. Now, many people didn't like this. In particular, I think there was a team writing in from Berkeley saying that they did the same experiment in the vacuum chamber. They saw exactly the same thing without, of course, the sound. Now, that's actually not conclusive proof because, as Maxwell knew, when you drop the density of the air or density of fluid, the viscosity does not drop. Because, you see, as the density drops, the mean free path, that's how the molecules, gets longer and longer and compensating for the expected drop in the viscosity and so forth. It's a mess. So I was a postdoc in Montreal in those days. I had already worked out a simple model of this, and I wanted to do an experiment. But a vacuum chamber is very expensive. So I went to a ladies' accessory shop and bought this. It is a bracelet, and there is no question of air trapped underneath a disk because there is no disk. So now I'm going to launch it in a nice way. I spun it vertically. It's like a ballerina spinning in a beautiful fashion. Let's call that the first phase of motion. Soon, the ballerina will become tired and will make a sudden transition, very interesting, to a second phase. And that second phase is exactly the same motion as that of a coin. We'll see. It's spinning and spinning, still vertical and still steady. That's, by the way, an interesting stability problem to analyze. But soon it will transit. You see she's getting more and more tired, slower and slower. Now, watch. Yeah, now the transition has occurred, and from then on, you can see that it's effectively the same motion as same physics as before. And there is no air trapped underneath the disk. There is no disk. It's just any bracelet. Oof. Okay, so what is happening? Well, energy must be dissipated, must go somewhere, because after all, in the beginning, it's moving very vigorously. At the end, nothing is moving. So energy must have gone somewhere. And that turns out to be crucial for that singularity, that divergence. So I'd like to show you where the energy goes. There are many different mechanisms, and they are all interesting to study, but one of them is as follows. As you see, the point of contact goes around. That's also the point of pressure, and so you are pressing in a periodic manner, and that makes the whole surface of support vibrate. You are sending out an elastic wave of vibration, if you like an earthquake of type, and it goes away to infinity and carries off energy and doesn't come back, bless you. So that turns out to be a significant mechanism for loss of energy. In order to prove which, I'd like to do another experiment. Let's do the same experiment, but on a good absorber, of elastic energy, such as a human body. You know, a human body, especially mine, has been designed to withstand all sorts of shocks. So when I do the same experiment on my hand, please see how long the experiment lasts. Ready? That's it. The entire energy escaped through my hand, through my body to the ground. We have effectively earthed the experiment. So that turns out to be a friction mechanism and the dissipation mechanism. And we'd like to now understand what is going on. Here is the analysis. We shall imagine that this motion can be decomposed into the spin and the flapping. In fact, it can. And then we'll evoke a very nice pictorial pattern. Whatever happened to my, here it is. Let's think about the bouncing ball. When you drop a ball, it goes bong, 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 bong. Beautiful example in elementary mathematics of an infinite series whose sum is finite. Boom, 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 boom. You know, it bounces more and more frequently, but then it stops in finite time. How does the nth bounce behave in terms of energy? Here's how. It's actually quite simple to see. The energy for the nth bounce is, of course, equal to the height. It behaves like the height to which it bounces back. It's the potential energy, if you like. Yeah? It scales like the height, but height scales like time squared because, you know, if you want to fall a certain height, you have to go in time squared. That's the falling pattern. But time is 1 over frequency, so we have the conclusion that the energy behaves like bouncing frequency to the minus power to minus 2. At the same time, there is a dissipation, which I said was very crucial. It can be due to, you know, vibrational wave and friction and so forth, but whatever it is, let's look at how the energy goes away, gets lost, gets wasted as a function of time. Except that we are going to measure the time towards the singularity. I denoted that singularity T sing because at that moment the object sings, you see, it's the T sing. Now, that's a constant, so it becomes minus d over dt of E, and we shall postulate, this is where the interesting physics is, that this dissipation is proportional to the flapping frequency. You can put another power of the frequency there, then the conclusion would be different. But here we shall assume that it's proportional to flap frequency, and then the rest is pure mathematics, because you see frequency, I'm identifying those two frequencies, is proportional to the energy minus power 1/2. So this becomes energy to minus 1/2. We can move there, and that's a separated differential equation. I can integrate it, and the result is that energy to power 3/2 behaves like the time to singularity, but I know what energy is in terms of frequency, so the final result is that frequency diverges near the singularity like with power minus 1/3. This is the prediction of the model. Now, Ariel Amir, who is a junior fellow at Harvard, recorded this experiment, and this is what you see. The vertical axis is the frequency, and time runs from right to left, because Ariel is from Israel, and I believe in Israel they run from right to left. But anyway, so this is and the red is the theoretical negative 1/3, and look at the data, that's the blue. Beautiful fit to the negative 1/3. I mean, you don't get clean data like this nowadays, right? I mean, it's absolutely amazing clean fit to negative 1/3. And this negative 1/3 power then is a fairly robust type of singularity, it turns out. Anytime you have a multiple collision, multiple bouncing situation, which dissipates energy and diverges, you get this kind of negative 1/3. As an example, here is a pair of magnets, very strong magnets made of neodymium, one of the most magnetizable elements in the universe. And when I put them next to each other, they do this. Yeah. I can toss them in the air. I'll do that again. I'll do that again. Maybe a little more. Yeah. Can you hear this? This zzz? That's the rising pitch, and that pitch, we recorded this last week, in fact, with Ariel. The data is not so clean as for the shattering disk, but the signature negative 3rd power is still there. So it's really a kind of very nice singularity model, which happens within finite time. And that is why this is all happening. Okay. Now, that was all about singularities of all sorts of kinds. Every once in a while, you run into somebody who happens to be carrying around an inclined plane, and he brings to you 2 jars. One of them is filled with rice from India, and the other one is filled with nice air from Princeton, New Jersey. So one is full and the other is empty, 1 and 0. And what we shall do is to roll these down the slope. And you can see that they roll down pretty fast. Not exactly at the same rate, perhaps, if you are sophisticated, you'll say, because the moment of inertia is doing something, but essentially at the same speed and quite fast. So what we'll do is to study how the speed of descent of these rolling jars, will depend on the amount of stuff which is inside, okay? When it's 1 and 0, it's quite high, it's quite fast, okay? What if it is 2/3, or depending on your optimism, when it's 1/3 empty, yeah? Or for that matter, 1/3 or 2/3 empty? What's going to happen? Let's try first 2/3. So when it's 1 or 0, they went down very fast. What do you think will happen to the 2/3 one? Will it go down faster than 0 and 1, or slower than 0 and 1? Or if you believe in the story of Galileo dropping 2 unequal masses from the Tower of Pisa, and they all dropped at the same rate, maybe the descent rate does not depend on the amount of stuff inside. So who thinks that the E2 go down 2/3 will go down faster than 0 or 1? Who thinks? Huh? Who thinks E2 go down slower? That's the option that most reasonable people go for. And who thinks that E2 not depend on the amount of stuff? Okay, so let's try this. Thank you very much. So we shall try this. Are you ready? I release, and it goes down very, very, very slowly. Yeah? Not only does it go down very slowly, there's a lot of stuff going on. It's a bit difficult to see from far away, but you see, there's a free surface along which there's a lot of landslide. Whereas in the rest of the jar, it's quite difficult to see, the grains stick to the interior of the jar. Only when they emerge on the free surface, they start sliding, avalanching, and then they dissipate a lot of energy. So in a nutshell, these grains are behaving like viscous fluid, usual, fluid. So that's something that we shall come back to, but let's, in the meantime, try 1/3. Now there are 4 possibilities, aren't there? So maybe it will be the champion, and it will be faster than everyone. Or maybe it's slowest, and it's slower than even 2/3. Or maybe it will be faster than 2/3, which was slow, but slower than 1 and 0. Or those people who have a beautifully symmetric mind might say, well, there might be some symmetry between f and 1 minus f, if you see what I mean. So maybe it will go down at the same rate as 2/3. So who thinks it will be the fastest? Who thinks it will go down the slowest? Who thinks it will be faster than 2/3 but slower than 1 and 0? That's the one that most reasonable people go for. And who thinks it will go down at the same rate as 2/3? Okay, so let's try this. Nothing up here and nothing up here. Shall we try? Oh! It stops completely dead. Not only does it stops so hard that even when I try to coax it to go down, it really doesn't want to go down. That is quite remarkable. What is happening, I'd like to then share with you. This phenomenon, by the way, I forgot to mention, because we are being recorded, I have to mention these things very carefully, that those heptagons that roll and don't roll were presents from Ruina, Andy Ruina of Cornell University. And this phenomenon was discovered by me, and it's being studied by Nicolas Taberlet, a very fine experimentalist in École Normale Supérieure of Lyon. So why did the jar which was almost full slow down? Slow down. And why did the jar, which was 1/3 full, immobilized? This has to do with a key property of grains. They can be sand, they can be rice, they can be anything flour. You see, when you go to a beach and try to make a pile of sand, it has to be dry sand, because with wet sand you can do all sorts of strange things, but dry sand. You can make the pile only so steep. If you try to make the pile steeper than that, it avalanches, it landslides, and becomes less steep. So the maximum angle, which here denoted by alpha, is called the angle of repose. That's where the sand pile reposes. By the way, the experts will know that the angle at which the avalanche starts and the angle at which the avalanche stops are slightly different, but that's irrelevant for our purposes. So we'll take just one angle of repose, and note that for liquid or fluid, the angle of repose is always 0. You can make a hump on the surface of, say, honey and so on, but if you wait long enough, it will become completely flat, and it will not tilt. So that's the angle of repose 0 for the fluid. Now, look at two scenarios. This is the scenario where the jar was 2/3 full, or jar is almost full. Then you see the point where the center of gravity is located is more or less in the center. At the same time, I denoted here by red the point of contact of the jar with the slope. And you can see that in this scenario, the gravity is on the downhill side of the point of contact. Then the effect of the gravity is to torque around this point of contact, is to rotate the jar clockwise in the picture. That is the direction that helps the descent. In contrast, if you have very few grains, the center of gravity of the grains might be on the uphill side of the point of contact, the red point. So the effect of the gravity, paradoxically, it's pulling down, but its effect is to rotate the jar counterclockwise, which is the uphill rotation, therefore which combats the descent. And that is why you can stabilize and you can make the whole thing stop. Note that this can happen because the angle of repose alpha is greater than this angle of inclination beta, and so it cannot happen, for example, for a fluid, liquid of any kind. Okay, so we have been trying to plot the descent rate, pace of descent, as a function of how full the thing is. And we saw that when it's 0 or 100%, it's quite high, but somewhere in the middle, there's a whole range, a whole basin of immobility. It's 0. That's quite remarkable. There's something even more disturbing about this. To the right of this, in other words, when you step aside and go towards 100, that was the experiment with 2/3, you remember? It went down quite slow. This is indicated by the fact that this point is lower than this point. It's slow, but we saw that there was a lot going on. There was an avalanche, there's a sort of very beautiful curve and so on, and grains stuck inside. So this is really behavior like a viscous fluid. Let's see what happens if I investigate this side. That is, if I start decreasing the amount of stuff towards 0, then the jar should start rolling. After when it's 0, it rolls. So what's going to happen when I try the very, very few grains? That's very few grains. Now what happens is quite remarkable. It sort of goes smoothly, but in a certain jerky motion. And again, it's kind of difficult to see on the camera, but there is no landslide inside the jar. The entire grains are moving back and sliding back and forth as if they were a single body, and there is no avalanche. So they're sliding inside, That's the behavior of an inviscid fluid. So what we see on that side, oops, what is this? On that, oops, there's no inviscid fluid. So on the left of this basin of immobility, you have inviscid situation. On the right, there is a viscous situation. Mathematically speaking, the theory of viscous fluids and the theory of inviscid fluids are totally incompatible. Boundary conditions are different, and there are lots and lots of problems, among other things, this singular limit, singular perturbation that we mentioned. So experimentally, what we are trying to do, interesting thing to do, is to fiddle with this so as to reduce this basin of immobility narrower and narrower and narrower, and finally make those two incompatible regimes touch. And then Mother Nature will have some really tough decision making to do. Okay. It is now time to bring this talk to a conclusion. We have covered lots and lots of interesting phenomena. In fact, I skipped one experiment, which I shall show during the reception. All those things that sound great and, in fact, are quite ill understood by even the modern science of today. Chiral Dynamics, friction as a creative agent, the phase transition, singular perturbation, finite time divergence, viscoelasticity we didn't see with an experiment, but inverse cascade and viscous and inviscid coalescence. Inverse cascade and viscoelasticity we didn't see. So all these things we can see in those experiments. That brings us to a really good question, which is, why are we playing with toys in the first place? By way of a hint to a response, I'd like to share with you an anecdote from Aristotle's little-known work called De Partibus Animalium. In there, Aristotle is talking about Heraclitus, who was a Greek natural philosopher of 600 BC. He flourished around that time. A big, big shot in those days, a celebrity, perhaps a professor at the Institute of Advanced Study of 600 BC. And two young people come to visit this professor and expect to find this professor, probably wearing a white lab coat in a very expensive laboratory and gigantic computer screen and then maybe a 3D printer and so forth. But then they're surprised to find him in a completely different manner. Aristotle says, in all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. And when they entered and saw him in the kitchen, warming himself at the stove and probably playing with the children, they hesitated. But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enagar kai entausa theus." To all of you who took the time to come here, and especially to Christine Taylor and Robert Dickhaff, who's the director of the Institute, and to organizers of this wonderful program, I'd like to extend my thanks and wish you a wonderful continuation of this great program, Women and Mathematics. Thank you very much.